And then I think we're good to go. Thanks again for being here, Kirsten.
Wonderful. Thanks for the nice introduction. And thank you all for having me. I'm really excited to get to talk with you all today. So today I'll be giving sort of a broad overview of a lot of my research, and kind of a central theme in that research is examining these trial by trial dynamics of visual attention and visual working memory. So, oops, gotta click here. Visual attention and visual working memory are really important cognitive abilities that help us achieve sort of complex goals and realistic visually guided behaviors. But one key feature of these important resources is that they also have a very limited capacity, right? So if we have a really big picture goal of saying like, I want to identify these flowers as I'm walking around the desert by San Diego, what I need to do is I need to select just a subset of information to hold in working memory. So that way, when I take my eyes away from this visually complex scene, I have this little bit of information in working memory that I can use to achieve my goal by, say, searching in this app for a color that matches the flower that I'm looking for. And there's been a lot of interest in studying individual differences in working memory and attention, in part because these are such key cognitive abilities for this mental workspace that we have for doing these behaviors. And so just, as a typical graph that we might see, oftentimes we'll try to estimate people's visual working memory capacity by showing them, say, a number of colored squares and asking them to remember them across a short delay. And what we see when we do studies like this is we get a pretty broad range of estimates. So we get capacity estimates that are ranging anywhere from only 1 item up to 5 items with a lot of variation in between. And part of the reason we're interested in these individual differences is because they do predict other important outcomes like academic achievement, things like this. And these abilities also tend to be disrupted in numerous clinical disorders. So working memory capacity in particular is disrupted in schizophrenia and Parkinson's and a lot of other disorders. Okay, so the broad organization of today's talk is, first, I'm going to talk about, this question of what is the capacity of working memory. We see there's individual differences in how many items it seems like people can store. And also this other question that's important for this same sort of integrated behavior of which part of this image will actually capture our attention as we're going about our goals. And typically, the way we think about these big picture questions has been a lot for convenience. How do we do this on average? And as the title of the talk suggested, today I want to consider how can we start to look at not just how are we doing these things on average, but how are these things fluctuating over time or changing as we encounter different things in the world around us. Okay, so starting with this question of capacity and thinking about the distinction between on average and trial by trial, oftentimes when we bring people in the lab to measure their visual working memory capacity, we show them a display like this. We're like, okay, remember as many of these colored squares as you can. And we don't just have them do this once, right? We want to reduce measurement errors. So we have people do this hundreds of times. And typically what we want to do, if we want to get a stable individual difference, is we'll just extract one average measure for each person, like their ratio of hits to false alarm is kind of their capacity estimate. But we also know that people are not robots. And I think in the human factors department, you will especially appreciate this. But probably people aren't sitting down and doing the trial exactly the same way every single time, but probably there's some natural variation in how they are able to do this task. So this brings us to this first question of how do these fluctuations of attention impact working memory capacity? And then in the second half of the talk, we'll turn our attention to fluctuations of what we're seeing in the world around us rather than to our own attentional state. Okay, so thinking about this question, how do we measure visual working memory capacity typically with a common task? As I kind of alluded to, a lot of times we like to use this change detection task. And there's a lot of good reasons to use this task because it's very easy to administer and it's very quick to do each trial. So we can get a lot of trials and really reduce our measurement error. And typically in a single trial, this task, what happens is I'll show you a bunch of colored squares for just a few hundred milliseconds. I'll ask you to remember them across a blank delay. And then at the end, we'll give you a test. So we'll probe just one of these locations and we'll say, is the color I'm showing you at this location the same or different from what it was before? Right, and like I already alluded to before, we get really reliable and stable individual differences. People can practice this task a lot and they all get better over time, but people tend to stay in their same group. So even when you practice, there is this stable individual difference where some people have better working memory capacity than other people. And anecdotally, historically in the literature, the way we've kind of conceptualized this is that if you are a low capacity individual, you can remember less stuff. You have less of a workspace to work with. So maybe that's why you have trouble achieving some of these complex behavior. You just can't hold as much information in mind. Whereas your higher capacity subject could maybe hold more. But when we're talking about this number of items, this is typically the average number that we're extracting from all of our trials. So an alternative model might be that actually both of our subjects have the same ceiling, where in theory, they have the same potential. They both could get 3 items and do really well at that. But what's different between them is how consistently they're doing that. So this case would also give this person an average capacity of 1 and this person an average capacity of 3, but the picture is a little bit different. This is really more about consistency rather than about that maximum ceiling per se. And if we look to other sort of big structural equation modeling studies with individual differences, we see hints that maybe a model like this might be plausible, right? So when we give people a bunch of different tasks, we see that people with lower working memory scores also tend to have things like more period of goal neglect or poor attentional control in like anti-saccade tasks and things like this. So it seems like these abilities of consistency of attention and working memory may be linked. But we want to look at this within the working memory task itself and see, okay, how is performance within this task actually fluctuating and maybe contributing to individual differences? All right, so to do this, we kind of need a slightly different task. And so what I've done is to do a variation of this change detection task that takes a little bit longer to respond, but gives us a much richer response. And why do we need to do this? Well, since in the change detection task, we're just probing people on one single item. So this makes it really hard to tell apart very different cognitive states. So people could be seeing these items and storing absolutely nothing, or they could be maxing out and doing a really good job and getting 4 out of 6. But if we happen to test them on one they didn't store, this is incorrect in both cases. So an alternative that we might want to think about is instead of just testing one item, we're going to have participants report all of the items. So the way this task works is it's sort of a 9 AFC at every location. So just as before, people see all the colored squares they're supposed to remember, they remember them across a blank delay. But now to report the items, people are going to use their computer mouse and click the color that belongs at each location. So for instance, this square up here is white, so they would click the little white part of this mass. And importantly, we're going to force people to respond to all 6 items, even if they feel like they don't have information in mind. This way we can model guessing later on. Okay, so now that we have this new richer measure, we can simply on each trial count how many items did people get correct. And just to like reiterate the approach difference between this and maybe other tasks that you might be used to seeing with working memory. In a typical change detection task or span task, typically what we do is we vary the external difficulty. So we'll give people lists or displays with 1 item, 2 items, 3 items, 4 items, and we'll randomly change how many items I ask you to remember on each given trial. And then we can see, okay, how well did you do when I really taxed you versus how well did you do when it was easy? Here, because we're interested in these fluctuations of performance, what we're going to do is instead, we're going to hold external difficulty completely constant. So we're going to give people like 300 trials of only set size 6 trials. And now our outcome is going to be how many items did they actually get correct out of 6. So first, we might just want to think, okay, if we think failures of attention are playing an important role in these working memory tasks, we first might want to simulate what would a total failure of attention look like in this task. And so we can model out if we make people respond to all 6 items and they're making a lot of responses, just by chance, they're at least going to get 1 correct half the time. So for the purposes of today's talk, we're going to operationalize anytime they get 0 or 1 correct, and we're going to call this a attentional lapse. And we can, by doing this, we can just look in our data and see how often are these types of things happening, and might they be important contributors to individual differences in working memory. Okay, so here I'm showing you a correlation of these lapse trials and the whole report task with a separate measure of working memory capacity. And as we'd expect, these are correlated. But another thing I would really like to point out is more so the scale of this y-axis. So here I'm showing the proportion of the trials in the whole report task where people are getting 0 or 1 correct out of 6. And we see that on average, this is like 11 or 12%, which really is pretty high. And we're also getting quite a range of individual differences where the best people are having basically no lapses in the whole session, and the worst people are having them, every couple trials or so. Okay, so is this really, I've kind of talked about this as either you're getting your working memory capacity or you're not. You're guessing from this completely information devoid state. And so is this what people are actually doing? And we can model what this might look like in our data. So before actually showing you the real data, I'm showing you, a thought exercise of what it would look like if people are either kind of engaged and getting their full capacity or disengaged. And so we're going to model this with just 2 parameters. So we can give people a capacity or how many items they get correct when they're in their on state. And so here I'm going to show you a capacity of 3. Because people are making so many responses, even if they only have a capacity of 3, we do get responses on the upper right part of this distribution from guessing inflation, where they're going to get some more right by chance just because of the number of responses that they're making. And when they're in this disengaged state, we might instead expect that they would be pulling from this guessing distribution, and we get kind of this bimodal distribution. If we fit this model blind to the true distribution of the data and just try to match the means, we can match the means pretty well by changing the height of the bars for how often people are engaged versus disengaged. All right, and it's possible this is too strong of a model. So instead we can also try a sort of partial lapse model where people aren't just fully engaged or fully disengaged, but really their attention is sort of waxing and waning over time, but there still is a maximum capacity that we can set as a parameter. And what's going to vary between people is how often they go below that capacity. So again, I'm just showing you some hypothetical outcomes based on trying to match the mean performance of what people actually got without looking at the underlying distribution. And again, so in this case, we would see that when you get your capacity, you get that plus some guessing. And then sometimes you're going to get below and you're in these sort of disengaged states. Okay, so what happens when we look at the real data? What kind of shape do we see, and what kind of differences do we find between individuals in terms of these capacity and attention parameters? So overall, here's the real data. So here I'm showing on the x-axis is how many correct out of 6, and the y-axis is the proportion of trials that they got that. And what's interesting is when we just do a sort of rough median split, we see that these groups tend to have the same modal tendency. They both get 3 correct most of the time, but they're really varying in how they're skewing around this modal tendency. When we do the formal modeling, we see that about 85% of our subjects are all fit by the same exact capacity parameter of 3. And that's more than you would expect from looking at the change detection distribution I showed you earlier, where really the bulk of the variance that we're seeing in our young, healthy college kids is driven by this consistency parameter rather than by this capacity parameter. Right, so like I just suggested, we see a wide range of individual differences in these failures, but it's not so simple as an all or none lapse where people are just either not doing the task at all. Instead, it seems like there's something more graded and gradual going on, and a large majority of people are modeled by the same capacity. Okay, so this is all great, but now we want to know, okay, so these lapses are happening very often, maybe 12% of our trials, which is quite a lot. So when are they happening? Is it the case that people are just, giving up at the end or taking a long time to learn the task and having a lot of failures at the beginning, or are they really kind of randomly sprinkled throughout the session? So to give you a big picture idea of this, I can show you this sort of performance raster plot where I'm going to show you all the data from the whole data set as little tick marks. So on the x-axis, we have the trial number over time in the session, and on each individual subject is a row of tick marks. So when they get 0 or 1 correct, we get a black tick mark. And when they do really well, we white tick mark. And we can see from looking at this that, first of all, I've sorted these subjects, so the worst performing subjects are on the bottom, and we see a wide range of individual differences in these black tick marks just as before. But also we see that these individual differences can't be explained by, say, our lower capacity subjects just giving up halfway through the session or things like this. These are kind of stable and stochastic individual differences and consistency that are happening throughout the session. So if these are happening often and unpredictably, we might want to know, okay, can we predict them to prevent them from happening? This might be a good long-term goal that maybe we could use some of our EEG tools for. And so to get at this question, we're going to have people do the exact same task, only now we're going to measure EEG while they're doing it. And we do a slight adaptation. So instead of remembering everything on the screen, first I cue you to one side of the display, then you remember just the items on the cued side. And using this lateralized design will allow us to take advantage of some previously characterized ERP components and oscillatory components that will allow us to get a handle on what is going wrong in this task. Because if we think about just one trial of this working memory task, there's really a lot that could go wrong, right? So people could have issues with maintaining control, they could fail to use this cue, they could fail to select the items, and they could fail to store the items. And so what we're going to do is use these previously characterized ERP components to see which, if any, of these processes are disrupted. So for the sake of the ERP plots, we're going to take our trials, and everything above that modal tendency, we're going to call good trials, and everything below it, we're going to call poor trials. And now we can examine what is going wrong when people are having these lapses. So one, kind of dumb but important possibility we wanted to rule out is kind of just, well, maybe people stopped looking at the screen. Maybe people are like, oh, like not paying attention and really, really not doing our task at all. And since we have EEG, we can check this out and we can make sure, okay, here's our difference between high and low case subjects when we use all trials. What if we get rid of all the trials where there's any sort of eye movement or blink, anything like this? And we see those differences are totally preserved. So participants do have their eyes open and pointed at the screen. This is not the crux issue with these lapses. What about something like pretrial control? It seems like these lapses are happening in sort of a graded fashion. And so we decided to look at frontal theta power, which has been a hypothesized marker of cognitive control in other tasks. And so here what we see, time 0 here is when the memory array comes up on the screen. So these negative times are times before the array has been shown, and then this is the maintenance period here. And what we see when we look at frontal theta power is a difference between good and bad trials that's starting even slightly before people have seen the items. So even before they've seen the memory array and are trying to encode it, there's already something starting to go awry with their control state, which maybe is leading to this bad performance. What about these other stages that we talked about? So obviously when they get this cue, they need to orient their attention to the correct side of space, and they actually need to select those items. So here we can look at the lateralized P1 component to see, did we get a difference where people are using the cue? And we see that yes, people actually are using the cue effectively and orienting their attention to the correct side of space. And they're grabbing those items as shown by an equivalent N2PC component. But what seems to be going wrong is sometime between this N2PC and actually getting those items into working memory. So we see the CDA component, which tracks the number of items stored in mind, is reduced when people are in a lapse state. All right, so what could be going on here? How can we make sense of this? I'm just going to kind of like wrap up this part here with a little discussion of this and say, well, we can predict these failures of attention and working memory even before working memory encoding. And this links in nicely with a lot of other work looking at frontal theta power as an index of cognitive control, and also behavioral findings that during these lapse states, we also see increased mind wandering and poorer metacognition. But these lapses are not totally monolithic. It's not like you can't do anything. So people are still using the cue and having a lateralized P1, but just not grabbing those items. So to me, it seems like since they're in this poor control state, it's kind of like they're like on autopilot. They are like able to use the cue and they're putting their attention over there, but they're kind of grabbing with slippery fingers and not actually forming those working memory representations with that visual information that is going through their visual cortex. All right, and just to reiterate home, here it really seems like consistency that we can see by looking at these trial by trial dynamics rather than capacity is really better explaining individual differences in working memory performance. Okay, so this wraps up the first section of the talk, which is really all about these internal fluctuations of attentional state and how that is going to really impact measures of working memory. In the second part of the talk, I'll tell you about more recent work that I've been interested in considering variation in what we're seeing in the world around us. So as I'm thinking about how these recent experiences can capture our attention. So when we think about visual search, right? So we're going to use this information we maybe have in working memory to deploy our attention to the world around us in order to achieve our goals. Fundamentally, this type of visual search behavior requires that we join together information that's out there in the world with information that's in our minds. And there are these different factors that affect our ability to really search and achieve our goals. So some of these factors are what we call stimulus-driven task factors. So this is parts of the image that are going to drive attention because of local stimulus differences. So for instance, this black sheep among white sheep. However, there are also factors that are goal-driven, where when we have a top-down goal of what we're looking for, this can really aid us in our search. And for example, if you haven't seen it yet, if I tell you, look for the odd mango out, that's like not very helpful. But if I tell you to look for the little birdie, that changes your ability to search this image pretty well. So in the lab, we often need to use simplified displays to control everything. So a popular analog for these visual search behaviors is to use an additional singleton task. And so in this type of task, we'll show people an array of shapes and we'll say, find the diamond shape as fast as you can, ignore color, doesn't matter, color will not help you. But we'll sometimes introduce color distractors, right? So your goal is just to find the diamond, but on some trials, there's this salient red singleton distractor. And a hallmark of distraction in this case is that you are slower when this red distractor is present than when it is absent. And so this is referred to as a search cost for distractor presence. And oftentimes in our models of search, we talk about, okay, is this a stimulus-driven task factor or a goal-driven task factor? But in recent years, there's been a lot of focus on this third task factor that doesn't perfectly neatly fit in to this goal versus stimulus dichotomy, but maybe falls somewhere in between. And we want to understand how this works, right? So to give you an illustration of this third task factor of stimulus history, just something unfolding in time around us in the environment, you can imagine that maybe you're going to the lab, pop in on weekend day, you're going to stop and get some coffee, and you walk out of the coffee shop and you see people dressed like this. And this would be very distracting, very salient, bright yellow and black stripes. You're like, okay, wow, that really caught my attention. That's very unusual. And then maybe you turn the corner and you see more people, and then you realize, there's a football match today, right? So as you see more and more of these, it becomes less and less distracting to you because you've seen it before. And the sort of visual search analog of this in the laboratory is that what happens when we change the colors around, right? So if we have the color of the non-targets is changing all the time, we get a really large reaction time cost. But if we hold the colors perfectly constant, you are no longer distracted. And the important thing about this is that actually, the stimulus pixel-wise saliency of these images should be the same, right? Because on this single trial, we see an identical image. But in this case, it's really distracting to have this red distractor here. And in this case, it's not, because we've seen the same colors before. So what is allowing us to not be distracted by this same exact distracting red item in this case, where we have this additional information of history over time? And I'm interested in how we do this in the brain and how this information might get integrated into what we call priority maps. So in a lot of models of visual search, what we think is going on is that we have stimulus-driven information coming in from, say, visual cortex. We have goal-driven information coming down from, say, PFC. And somewhere in the middle, we have this priority map where we're integrating all of this information together in a spatially organized fashion. So what I want to ask today is, might we exploit either of these two existing mechanisms in order to suppress these salient distractors when they're repeated over time? Right, so both of these seem pretty plausible and have been debated at length in the literature, right? So in a goal-driven account, we might say, okay, I've seen a lot of yellow and vertical things. I should really expect that, and I'm not going to be distracted by it. I kind of have an awareness that I should reject these distractors because I've seen them a lot before. But another possibility is that these distractors could be modulated by just stimulus-driven mechanisms. So passive exposure might sort of modulate your early visual responses to these distractors, making them less salient. Okay, so how might we look at this in the brain? And of course, I kind of painted this picture like, oh, this priority map is just in one place, and this area cares about goals, and this area cares about stimulus. But the truth of the matter is that most brain areas care about goals and the stimulus to some degree, but there's variance in how much they care, right? So if we're looking from V1 up through IPS, we know that areas like IPS have much stronger goal-driven responses than areas like V1. And the reverse is true of stimulus-driven responses. So V1 is going to have a much stronger stimulus-driven response than a later area like IPS. So in the paper, we look at all of these areas and see how they're changing with repeated distractors. But for today's talk, I'm just going to focus on these two endpoints because they'll give us the best handle on whether something is really a goal-driven or a stimulus-driven modulation. All right, so how are we going to look and see in the brain how people are learning to suppress these salient distractors? So with the general approach they're going to use is to train a model that will allow us to decode the attention to each of the items in the search array. So we're going to first train our model on just some of these checkerboard stimuli that are at different positions in space. And we're going to do this for each retinotopically organized region of interest, ranging from V1 up through IPS 0. Right. Sorry, my Slack notifications are going off. But yeah, all right, so we're going to show people a bunch of these checkerboard positions, and we'll say, okay, for this little voxel here in V1, we know that it really liked this 12 o'clock position and this 1 o'clock position. So we're going to give it stronger weights for certain spatial positions. And we do this for all of our voxels. We know which spatial positions each voxel kind of likes. So now on some of our held out data, we can see, okay, how much is each voxel responding? And we can use those weights we established with the other data to get an estimate of what item people are actually attending to right now. So the first thing is we just want to do a sanity check. So if we show people one location, can we read out the other location? And we see that, yes, we can do this really well. We get really nice responses that are spatially organized for these checkerboard stimuli. But now the critical thing is we're going to train the model on this one item data, but then we're going to test the model and see what happens to 4 items at the same time, right? So training the model on this one item with this checkerboard, and then we're going to show it our visual search data, and we can get estimates of how well represented each of these search array locations is. So we could just quantify how high is the peak for this distractor item versus this target item versus these non-target items. And by doing this, this will now allow us to ask questions about what is changing with stimulus history. Are we seeing changes to the target representation or changes to the distractor representation, or both? So the critical aspect of the design for this is that we're always going to be comparing arrays that are physically identical so that the stimulus-driven aspect of our bold response is identical. But what's going to differ between conditions is what happened before that critical trial. So in the color variable condition, we're going to see the colors of the non-targets and the distractor are swapping randomly from trial to trial, and we get really robust capture in this case. In the color constant condition, throughout the run, the colors are held constant so that people can learn to suppress the distractor. And now we can look and see, okay, do we see a goal-driven response where people are enhancing that target representation to better do the search task, or are they actually able to suppress this distractor representation? And just here's that behavior just to show you that this behaves as expected in our scanner subjects where we get capture in the color variable case, but not when the colors are repeated. All right, so here I'm going to show you these model estimates of how well each of these item positions is represented in these sort of two endpoint areas. So like I talked about, IPS is going to have much stronger goal-driven responses. V1 will have much stronger stimulus-driven responses. So looking at IPS, what we see is that we do see strong target prioritization, just like we expect from numerous other studies that have shown that when you prioritize a target, you get a larger response in IPS. However, this target enhancement wasn't actually modulated by the history factor. So color constant is represented by these purple lines and color variable is represented by these green lines. So the target is always bigger than the distractor here, indicating target related enhancement, but these purple and green are equivalent in IPS. In contrast, when we look in V1, like we'd expect, we don't really see goal-driven target enhancement in V1 in this study, but we do see an attenuation of the distractor signal when the colors are repeated. And this attenuation effect is specific to the distractor location rather than to any of the other locations. Great. Okay, so this seems to point to a sort of early stimulus-driven attenuation of the distractors starting in V1, rather than a deliberate goal-driven suppression of the distractor. So how might this happen? And this is sort of a fun thing to think about that we'll need to test with future modeling, but here's some ideas that we have right now, right? So one idea how this might happen in sort of a stimulus-driven fashion is that stimulus repetitions might lead to sort of neuronal adaptation in early visual areas. And this adaptation could alter inter-item competition that is really important for saliency computations. Okay, and let's unpack what that means a little bit here. So when you think about saliency computations, what makes this red salient distractor really salient? And what seems to be important is the number of other items, right? So if we just have one blue and one green item here, neither one of these is particularly winning out over the other, assuming they're like fairly isoluminate and things like that. But if we increase the number of blue items, now the green item is going to be a lot more salient. And one idea for why this might be is that these blue items will inhibit one another, leading this green item to actually be more salient. And there's some ideas that these kind of saliency computations could be happening, as early as V1, where these competitive interactions within V1 could be sufficient for an image computable saliency map. Although I'll say this isn't mutually exclusive, like we might also see saliency computations at many stages of the visual pathway, but plausibly this could be starting here as well. And so what predictions would we make from these types of competition? So one behavioral prediction that we make is that when the distractor and the target are close together, they should compete more compared to when the distractor and the target are on opposite sides. And that's exactly what we see in our behavioral data as well. Right, so competition is important, and maybe by changing this competition over time, we could change salience. So when we think about two-dimensional salience maps, like Edie and Cook style, we already are integrating spikes over some period of time in order to estimate which parts of these images are salient. So what we might want to do is just, to consider a longer term change to the spiking activity that could alter the computations. So for example, this would explain why when we get these pop-out effects that we see, things unfolding over time, over much longer time scales, can really contribute to our saliency computations. So if we think of just a 2D saliency map, obviously these two images would have the same salience, right? But if we integrate a lot more over time, we could see that this would explain why we get different salience when it's all blue items compared to a bunch of green and then blue. So in the context of these multi-item displays, this gets a little more complicated, but one idea is that when you repeat the same colors of displays over and over, you could weaken this inner item competition and actually make the distractor a little less salient. Okay, so there's a caveat that this doesn't work for other distractor types like reward and things like this, but I think it's a really fun idea that will be great to explore more and model a bit more formally. Okay, so bringing things sort of full circle here and to come to some sort of big picture questions, to maybe kick off some discussion with you all. Today we've talked about how these trial by trial dynamics are important for understanding working memory and attention. So in the first half of the talk, we talked about how these internal fluctuations of attention really are very critical for individual differences in working memory. And in the second part of the talk, we talked about how external stimulus dynamics can shape what parts of an image are actually salient. And again, as always, we're always using these things in tandem, right? So in this example that we opened with, in order to achieve really complex behaviors, despite our limited processing capacity, we can't hold all of this information in mind. So we select just a subset to then deploy and use for our goals. All right, so some sort of big picture questions to close with. So first, with this consistency versus capacity thing, there has been a lot of work that's been really interested in training working memory capacity. So a question I want to pose is maybe, is it useful to train working memory capacity and trying to increase the ceiling? Or would we be better off with a lower stakes goal of just saying, let's try to reduce failures. So by just eliminating trials where people get 0 correct, that would actually move people up into like the next sort of group. And then of course, all of this work was also done with healthy young college students. So I'm also interested in whether capacity or consistency is actually disrupted in clinical disorders. Among healthy college students, we see the vast majority of individual differences are explained just by consistency, but this might not be the case in more profound deficits. Right, and then in the second half of the talk, we talked about these external stimulus dynamics. So I'd be interested in figuring out, okay, what's the time course of this temporal integration that's happening over a really long time and contributing to our saliency computations in the moment? And can expectations ever act counter to this? In our task design, we didn't really give expectations good opportunity to do this, but I'd be curious to see what happens. Right, and then in future work, I want to ask how these things are interacting. So how is the stimulus history interacting with what gets prioritized within working memory and how working memory and visual search are interacting? Okay, so just leaving those for some food for thought. And with that, I'll say thank you to our funding. All these data are all on Open Science Framework if anyone is interested in checking them out or downloading them. And then thank you to you all for your attention and for having me here for your colloquium.